Welcome to Foresight's Molecular Machines Group. I'm really excited to welcome Boris here again. He joined us recently for an in-person small path to progress workshop. And before that, we met at our last workshop, the proper molecular machines workshop last year. We're really a big fan of your work and we're super, super excited about all the progress that you've been making now within a new organizational structure. And today you'll be discussing predictive molecular simulation, and I'll share a lot more about you and your work here in the chat, but feel free to just take it away.
Thank you. That's awesome. That's great. Foresight has been amazing. And actually, we met our investors at Foresight, so we thank you all a great deal. We owe you a lot. Freecurve Labs is a company that's designed to commercialize predictive molecular simulation. Let's discuss a little bit simulation and its nature. Simulation, in one way or another, whether on pen and paper or on computer, has really revolutionized our world. Everything we see today has been tested, simulated, and predicted, and then built in real life with laws of electricity and magnetism, with laws of gravitation. We just take it for granted. Even special relativity. In your GPS in your phone, there's a little correction for relativistic effects, and that actually makes a difference for your GPS. And that's how precise physics is, and that's how precise physics should be. But a large part of our world is made up of everything, actually. The joke is, don't trust molecules, they make up everything. Molecules make up everything, and their behavior is governed by laws of quantum mechanics. This is absolutely known and correct. But despite having the laws, because quantum mechanics is really intractable for large systems, we cannot actually model or predict properly the behavior of something as simple as dissolving sugar in water, much less complex biological mechanisms, which is actually what this workshop is all about. So in my example, dissolving just sugar in coffee with state-of-the-art tools today will give you an error which is approximately 10 times the error that a medicinal chemist would expect you to have to actually listen to what you're saying when they're making a drug. Just something as simple as sugar and coffee. When you go to things like ionic systems, which are incredibly important, batteries, so on, the error gets much bigger, and the errors you get are roughly half the temperature of the sun, which is completely unusable. There are no tools that are used for ionic systems and energy storage from simulation. This slide is a little complicated, so I might just gloss over it, but it says that when you do ligand, protein, drug design, although people try to tell you that it's working, actually for every single system, it's essentially a random number. Recently, we've had a really beautiful explosion of activity in structural information, which started with the protein data bank, and with the use of AI and everyone's sort of AlphaFold, has extracted a lot of structural information from the PDB. But in fact, these amazing tools do not have inference to anything other than what they came from, which is 21 functional groups of a protein. And they have no correlation, even by design, to any energy or wanting to be near something. And so as expected, their predictive abilities are actually zero, completely zero, in several avenues. I want to take a little step back and tell you why this problem is actually very difficult. This problem is very difficult especially for biology, because biology is complex and intricate, and it has a very rich behavior. And in order to do that with fairly simple building blocks of chemistry, the trick is to use very large numbers to barely offset each other to create the final small result that can drastically change based on the component. I'll give you an example. So this is a typical drug design trial where you just substitute a benzene for a chlorobenzene next to an amino acid. The energies involved in this little substitution are as big as 30, 40 kilocalories per mole in each direction. And there are much more of them than I put here. The total answer, the final answer that a medicinal chemist or an experiment will need to get is 2. So the 2 is not actually a 2. The 2 is plus 55 minus 53 plus 100 minus 102, and so on. Because of this, beyond a certain level of accuracy, you're not getting less information. You're getting no information. It's like going to an optometrist and trying to read a chart when you don't have the right glasses. Until some point, you just don't read the chart. You can't understand what's going on. Quantum computing is another little side. The only thing I want to say about quantum computing is actually spectacularly bad at computing quantum mechanics, but good at a lot of other stuff. And that's probably a whole other topic and a whole other talk. This is known to be, since we are commercial app dimension value, this is known to be a hard problem. The market value of companies that do simulations, which essentially beautifully package up laws that have existed since the 16, 17, 18, and 1900s, like Bernoulli's equation, are, whether you count it $300 billion, if you put in aircraft design, probably $600 billion. The leader in molecular simulation, Schrodinger, has a market cap of actually now $1.6 billion. And the only reason they have that is because one arm of them made a drug via regular means, okay? The market for just cryo-EM imaging, just taking a snapshot of a protein or a protein with a ligand, is 1.2 billion per year. Binding assays, just saying does this molecule bind to a protein, 10 billion a year. From scientists and from economics and finance, we see that molecular modeling is not here. There have been some predictions, and this was thought to have been enabled by 2070. And this is just my little slide that says that the group I work with has done it now. Okay. So I will pause here for any questions, because next we're going to tell you how we did it. That's our next part of the talk. Are there any questions about anything I said here today? I think your mic is muted. Yes.
So you're saying that AlphaFold and RosettaFold are not giving accurate predictions?
More refined. Accurate predictions of what? They are, first of all, accurate, not exactly. It is virtually impossible to fold a protein from physics because it's purposely so flimsy. That's just the thing we actually know internally. However, biology has followed very interesting and repeatable and noticeable trends in designing proteins. And there are only 21 functional groups, and there are a lot of structures. So there's a lot of information about proteins and pieces of proteins being together. I think I have a good analogy. So at 5:30 in downtown San Francisco on a BART train, two people sit together a lot, all the time. And AlphaFold says that's how they want to be. But that's only because it's 5:30 and they just got off work and there's a BART train in their seats. If they were to walk around in the park, they might not want to talk to each other at all, might not even be in the same park. So that's roughly the analogy. Does that make sense? Mm-hmm. Mm-hmm. Yeah. Any other questions?
Can you just back up one slide, please?
Absolutely. Oh, yes. Go ahead. This one or before?
No, this is the one. I just wanted to see it a little better.
No worries.
Some of what you're showing is what you're forecasting you'll do.
That isn't my forecast. So Professor Haug at UCLA wrote sort of a forecast in 2017 and revised it in 2019. And a lot of about half of the stuff in their forecast has to do with quantum mechanics itself, with computation, DFT and so on, and half of it had to do with molecular modeling. And he predicts, I would not have the order as he put it, but he predicted that this would be actually enabled sometime in 2070.
I would love to hear Ray Kurzweil's take on that. I have a feeling it would move up quite a bit. But anyway.
When people say things like that, they obviously can't give you the actual date. But what this probably means is not in the next 10 years, because we don't know how, but not in 100 years. That this is roughly what he's saying.
Yeah.
Yeah.
It'll be on a Tuesday.
Right. It's difficult. It's difficult to make predictions, especially about the future.
Yeah. That's why you create the future. Anyway.
Correct.
Thanks. That's what I wanted to cover.
Yeah. No problem. And also since we're on the slide, I want to point out that the Monte Carlo method, which is ubiquitous and everywhere, was invented at the Manhattan Project for Molecular Simulation. Okay. The solution isn't really mysterious.
Oh,
can you guys see it? Oh, yes, please go ahead.
Yeah, there's Todd and Brenda who had questions. I think Brenda was first.
Boris, in answering Ted's question, you
Yes.
basically hit it right. But I did want to make sure that you're careful in your wording. Particularly AlphaFold 3 can certainly predict binding because there's a ton of binding data from FR data that's deposited and other kinds of crystallographic data that's deposited. It's a question of how much
No,
it is.
again, I would disagree with you. There's about 10 to the 8th not enough binding data that you would need to actually energetically predict it. It's a possibility. It's really good for something like our tools because we can check if that's true, or we can go from there to something that's more real.
Sure.
But it isn't actually in any way an energetic prediction whatsoever.
I'm not going to argue about the energetic now. I guess what I'm just trying to say is people made these same arguments about protein structure 10 years ago, that AlphaFold and things like this would not be able to do it. But the point is, with sufficient data, which in principle there could be, this will likely happen in the...
I'm going to disagree. In principle, and we have seen it internally, you will never get sufficient data for ligand binding from experiments. And furthermore, for ionic systems, it is not possible in principle to get any data. You cannot hold an ion in your hand. You cannot measure it. In the whole history of science, they've been 3 or 4 ionic measurements: the pH of water, solidation of lithium, and a couple of electrolytes, and that's it. So the only way to get sufficient data, which we'll see in a second, is to compute it. So I'm not disagreeing that AlphaFold is brilliant, and it tells us the possibilities of arrangements and very likelihoods of arrangements. But when it gets down to the actual energetic predictions, it isn't really a thing. The meta studies I showed show that, not just no correlation, not even a correlation. You can see Nature 2023, Nature 2024, they checked it out for ligands. It's a way things could be. Sometimes they are and sometimes they aren't. But these meta studies show by all those methods that there's no correlation. So we can take that offline as well, but I have to, Next, Tad.
Yeah, thanks. I think this would be a quick question. On your point about the usefulness of quantum computing, potentially.
Yeah.
I was wondering whether that could be useful for force fields of small molecules, or are you thinking we need to wait for fault-tolerant computers first before it would be useful?
I'm not an expert in quantum computing by any means. Actually, I'm not an expert in a lot of things. Currently, the way you would do force fields on quantum computers would scale as, I have it here, like 10 to the 3rd or something like that. Whereas regular computing force field scale is n log n because of the eVolt summations. So and I'm not here to say that tomorrow someone may not tell us how to map QM onto quantum computers properly or force fields. And we're not experts in this, so we can't tell you we will do it. Someone may do it tomorrow. Someone may do it in 100 years. Someone may never do it. I don't know.
Yeah, I don't think tomorrow is likely, but yeah.
Exactly. But it comes up, and the really weird thing is quantum computers are not good at computing quantum mechanics. Maybe because we designed computational quantum mechanics to be executed on normal computers. Maybe it's our fault, but I don't know. Yeah, great
Something
question.
for us to learn. Yeah, thank you.
Yeah. So anyhow, the name of the game is, as it has always been in physics, is to make an equivalent system that's tractable, whose energy is equal to the quantum energy of that system. That's it. We're not super geniuses. This is what we're trying to do. And now I want to remind you again that equivalence has to be surprisingly high. And that's why AlphaFold will have problems, because moving things by a quarter angstrom will just change things drastically. But they're a great starting point for simulation because we can't fold a protein from scratch. So why not start with an AlphaFold prediction? So I'm going to go a little nerdy here, but hopefully there's enough graphics to make it worthwhile. One way to look at the energy of a system of many things is to break it up into its components, doubles, triples, quadruples, and so on. It's just the way, one of the physics expansions. And so our group started with making sure that all the terms past the first term were correct for several reasons. So in physics, there's a concept called polarization, which is the mutual influence of two things on each other. It's not dissimilar to how magnets work. It's exactly how magnets work. But polarization has a very beautiful property. as does all physics. Imagine, which is really important compared to AI these days. So in physics, if you know your behavior is a straight line, your training set is just 2 points. Whereas I have drawn a straight line with a perceptron and it takes 30,000 points. So polarization, if you do it properly, you look at it properly, extract properly, allows you to do a quantum computation on sets of 2 molecules only, which is actually really tractable. There's a lot of those pairs, but it's tractable. And then it lets you properly model a system of as many molecules as you want, if you do this correctly. This is a key concept. And this slide actually shows in Nature that we've done this properly. It actually does work. Our team is amazing, and they've extracted that inference correctly. Physics has amazing inference, if you get it right. Amazing inference. Remember I said that you have to be shockingly precise. So the next thing that the group did is to take a look at the very first term. Now, the first term is still the workhorse of most molecular simulations today, except for some advanced ones. They were invented in the 60s and 70s by our colleague, Michael Levitt, who is part of this company, and Parplus. And so we tried to be incredibly clever, and we went from something like above, simple van der Waals, Leonard-Jones potential, to something 5 times more complicated than is shown below. We are super clever. We can write really nice formulas, and let's see if we can capture everything with these formulas. So remember, enabling polarization and making this really complex, we achieved significant success. We could take anything neutral and dissolve it in anything else neutral for the first time from first principles and get the right answer. This is a first, and that was really satisfying. Not fitting to experiment, not trying to match something up, just starting with quantum mechanics and getting the right answer for dissolving things and things. So we were really excited, and we went into life, protein systems, and we failed spectacularly because, and I've said this 2 times already, the level of accuracy was just shockingly high. That was necessary. Also, we went into energy storage, and our predictions were off also by half the temperature of the sun. So it was really disappointing. And I want to skip a lot of details, but actually, since I've criticized AI so much, I want to say, no, it's actually amazing. The remaining bit here was to actually add a little bit of neural networks to the physics. Physics has amazing inference. A neural net doesn't know what an electric field is. So if you put your trained system into a battery, it will just have no idea what happened. So physics is amazing, but there is actually a point when you're translating quantum mechanics and Newtonian mechanics, the final bit that you just cannot encode in any formula or any Bézier curve or anything like that. It just has to come from a flexible, computable thing like a neuron. And that some proprietary sort of fingerprints and neuron AI stuff, this slide shows that while keeping all the physics and adding a little bit of a neural network component, we were able to get the error between the quantum mechanical energy and our system energy effectively down to 0. It's just amazing. And when we did that, all kinds of miracles happened. All of our protein ligand simulations became absolutely correct. All of our ionic systems, the 3 or 4 measurements that I mentioned, but also you can also dissolve salts, and there's 2 ion things there that you can see if you add correctly. The chances of you adding them, the chances of getting the right answer are virtually 0 if you're not right. Everything became beautifully correct. And that's basically it. Just to summarize, essentially, there's a way here to extract quantum mechanical interaction information from sets of 2 molecules, which is tractable, and through a bunch of very beautiful techniques to make it work and applicable to large molecular systems correctly, predictively, as we expect from physics. Okay? So I think that's why in 2022, we can say we did it. I'm going to pause here again, because now we're going to talk about the company for a second. And I can go back to any physics slide that is desired. And also just want to say, the questions I love the most are the ones where we disagree. I do not want to leave this meeting, for example, with the AlphaFold question, to say that we argued, it is actually in disagreement where most things move forward. So I really appreciate it.
Come on, you guys, your chance to haggle.
Okay.
Brenda's hand. Brenda, go for it.
No, I'm not trying to haggle at all. I'm just trying to. So in terms of what are you doing for the many-body expansion? So is this similar to like Paisani's work with the many-body expansions?
So that's a very good question. So Paisani's work is actually intractable. This is a very good question. Fantastic question. So Paisani is going out and explicitly including the 3 and 4 body terms. And that's the reason. And the number of, if you have the richness of chemistry, and then you want to take all quadruples of it in every combination, that is completely intractable. You know, in Paisani's work, that's the reason why Paisani started with water 15 years ago, and then 15 years later, maybe an ion. It's just not doable, especially at the level of accuracy like coupled cluster. Whereas our work extracts the many-body expansion from dimer calculations only and some monomer electric field perturbations. That's the difference. We do not need to explicitly go to trimers, tetramers. We do it all at once from the dimer calculation. This is a fantastic question.
Interesting. But then you end up with a couple cluster expansion of dimers, right? So dimers with dimers.
Dimers. Yeah, dimers. There's a lot of them, right? A lot. Not few, right? So to cover 80% of drug bank would be like 300 by 300 interactions. It's a lot. And also recall that it's not just a dimer calculation. You have to try it in many orientations and combinations. For example, here, this is just water and water, and every dot here, there's 30,000 dots, is a relative orientation and then a distance. So there's a lot of calculation. However, this is actually a fantastic question. Yeah, thank you.
Yeah, thanks. I think that's a very useful answer. You obviously know this, but because
you obviously know this.
The intractability of the other terms is a huge problem. And particularly if you could do everything from dimers, then you actually could talk about accelerating with machine learning and other things, right? Or doing things on.
And also, this is a more technical deal, but you have amazing knowledge. So thank you very much for asking and for being here. The way we've done it, I just found on these slides, is you can enable it piece by piece. So you don't have to do everything. You can say, let's start with charge interactions first. So you can incrementally, you can start going forward without having to do everything, as in some current AI models, right? So, yeah.
Okay, I think we can continue. There's more and more people joining this seminar even.
I know, they're coming. We're physicists, so they missed the funnest part. Thank you for that question. That's really good. That's great. Amazing. So the next part is a little commercial, so I apologize, but we are a company. We started this as a focused research organization science effort. A very wealthy individual just gave us not unlimited, but not so much the money, but the freedom to take what looks like as long as we need, a decade to figure this out without having to publish, without much pressure. So that was really amazing. And then when we were done, which was a year ago, the mandate was to go and see if we can commercialize it. It's one idea. There are other ways to go. And the original project, actually not mine or our group's, the original project was Michael Levitt's idea. He's been trying to do it since 5 in various ways because he didn't think that academia had the right incentives. In academia, you want to say something about a thing. And he wanted to put a lot of pressure on a group by saying, you don't have to say anything about a thing until we actually solve the thing. And that was the original idea behind the project before commercialization and Freecurve Labs spin out. We want to try, so Brenda, right? Your question was phenomenal because we will enable interactions piecewise. The first thing, as you say, that we want to do and give it to the hands of people are atomic level refinement of protein structures, like starting with AlphaFold predictions or an existing snapshot. It's a very nice and useful thing. We also want to have an energy product out this quite soon. So electrolyte composition analysis, what's better, what's less, what's more conductive, some other features. And after we raise our seed round, we will start enabling intermolecular interactions for all chemical groups, and we'll be able to have a ligand assay, a virtual binding assay, and a lot of other products. So I think that's it. We have an amazing core team. Our advisors and investors are leaders in commercializing and scientific simulation, people like Woody Sherman. Our co-founder is incredibly famous, so we don't get to hang out with him as much as we want to, but he still talks to us about science all the time. And we spun out. We're almost finished raising our pre-seed round, and we're going to have a seed round planned for September 2024. So if you know anyone who's interested in supporting this commercially, please put us in touch. That's it. Thank you very much.
Fantastic. Thank you so much. We already have the first few hand raises. Are you okay taking questions already?
I have all the time. Yeah, I got through a lot of slides in 1 hour with questions. So we're really good. Yeah, please. Yeah.
Okay, Micah, you take it away then.
AI sometimes can be extremely expensive to run. I'm curious, how expensive and time consuming is it to do something like verify an AlphaFold output or some other useful piece of work? Is this something that's going to take like 3 months of 10,000 GPUs, or is it something you can do like on a home computer in an hour?
Home computers are changing quite rapidly, right? It's an interesting question, but this is a polarizable force field. So it's about 4 or 5 times slower than current force fields, which on Anton can run microseconds or more. So it's about 4 to 6 times slower because of polarization. And the AI component, again, it's a little technical because like one of the reasons LLMs are so huge is because there's actually no structure underneath it. Like when you have a predictive model for chess, there's chess rules in it. But LLMs are gigantic because you don't have grammar or not much grammar or meaning there. And so you need enormous systems. But because we have a lot of physics, and also when I talk to Brenda, because we enable things in increments, the actual AI component is about as fast as the polarizable force field. It slows it down by a factor of 2 if you don't actually parallelize it properly. So that's not really a hit on anything. Also to that question, sampling is a really huge issue in condensed phase systems. So the best way to enhance sampling is not always just to run longer or faster. There are also quite a few physics tricks to probe regions of your system's phase space that are not just by waiting. So that's a complicated topic, but we do have them and other people have those techniques.
Any other follow-up? Otherwise, I'll go over to Jeremy. No?
No,
Cool.
good, thanks.
Okay. Awesome. We get a thumbs up. Jeremy, you're next.
No problem. Thank you, Allison. Very cool, Boris. Additional technical details. Nice. Out of curiosity, when do we get to the point where we might be able to simulate dynamics? ATP hydrolysis changes the electrostatic.
This is a really fantastic question. Oh my gosh. Fantastic. Some of my colleagues on this call are smiling like ear to ear right now. May I be a little technical here, or is that okay? One of the key papers in the original Nobel Prize citation from Michael Levitt is actually, now we know a crude model of enzyme action, which is really key. Essentially, it says that the enzyme strains things to enable the reactions to happen. So our techniques do not currently include the actual reactions, nor do they need to, because they happen when they happen and very quickly. But in order to model an enzyme, you would essentially need to model the intermediate states and their relative probabilities and populations. For example, pre-reaction in enzyme and of course water, and then of course post, and see at which, because of the enzyme, does that actually shift to the other molecule. And so as a precursor to that, we've actually computed the pH of water in water, right? So how stable are ionic species of water, hydronium, in water from first principles like this? And it's an hour or 2 on the computer, whatever. And they were spectacularly correct. Water is indeed 14. So in principle, once we enable the computation of other interactions, we can see how enzyme action allows these things to proceed by properly. This is where accuracy is really important. Because of this accuracy, we're able to evaluate the intermediate states for the reaction in the enzyme, and we can see if it works or not. We can improve it. That's actually, a great question. And like, if you look at the roadmap, I think, okay, again, my colleagues would like nothing better to go do it in the next 6 months or a year, but there is a computational cost to, as you understand by now, hashing up quantum mechanics, because that's what we're doing. So you have to do quite a bit of computing. Not that much, is protein, water, and then the things you're looking at. But we are commercial, so we have to focus on some other stuff. But the fastest it could happen with just, let's say, the computes that we want to get would be in a year, we could redo Michael's original paper, but actually put numbers to the reasoning. Yeah.
Very cool. Thank you.
Thank you.
Awesome. Steve.
You said that you do dimer interactions, and I'm presuming you have to put some limit on that. If you have 1 million molecules, you don't do 1 trillion comparisons, right? Do you do that out to some threshold of error, or you go farther and farther away until you get to some threshold of change?
Right.
Right.
So there's something here. I glossed over a lot of technical details, which we didn't invent, but they're state of the art for a long time. So we don't actually compute pairs of molecules. We compute pairs of sort of functional groups and the minimum molecule that contains it. And we have, and also other force field developers have for a long time had, ways of joining those. There's a reason functional groups exist, and people use that term in chemistry. They do have a set of properties that is self-contained, even if you join them to another thing. So, for example, a rotable bond can be cut and capped and then joined back together with some tricks to actually keep all the properties intact. So when I said pair of molecules, I really meant pair of functional groups and some permutations of them, not every possible molecule, not trillions. To cover, again, all molecules that have ever been made for chemistry and drugs, that's about 300 functional groups or so.
Okay, thanks.
Happy? All right. Feel free to add any questions or comments that you guys may have. Other than that, I have a few just like standard questions that people really love to answer to usually. The first one is, if you project like about 5 years out, you mentioned that you have been given more like a 10-year timeline here, which is great. But in 5 years or something, where do you guys hope to be if everything goes well, if you raise the funding and if things are chugging along like relatively expectedly?
Actually, in 5 years, I think in 3, the only roadblock to us moving fast is part of hiring, because physics is becoming a rare skill. There's a lot of other people you can hire, but real physicists are becoming rare. And some part of this group has to be that. We have most of them. But in 3 to 4 years, we will be able to refine protein structures, do virtual assays for drug design, simulate battery systems. I don't know, depending on who wants it, maybe desalination membranes. There's going to be a general engine for doing predictive molecular computing. So I think 3.5 years is all we need, because doing research is really easy in hindsight. But when you go forward, it's 9 times out of 10, you're wrong and you hit your head against the wall. But everything from here on out, maybe with the exception of a little transfer learning to make less computation needed, is just technology. So technology can be accelerated with management and money. So I'm not really that concerned about that.
Awesome. And if there are any challenges where you're not quite sure, well, if you want to solicit help from people that are not joining your company, but nevertheless be like, those are really important problems that we still need to crack on this path. Is there anything in particular that you want to point out?
This would be more technical, I think, or more physics technical. There are systems which are really important, like graphene, that actually do not have adequate quantum mechanical computational descriptions of them. So if anyone wants to do that, would be super, super cool. And I think, well, Igor, of course, sampling techniques. We are just ourselves playing with them. But if anyone will come and use AI, which has recently been done, to actually make a microsecond simulation effectively last 20 nanoseconds, but actually sample everything properly, that would be a wonderful complement to our work. Yep.
Okay, great. Love it that you're soliciting help here. And then you've already mentioned a little bit like what you're raising now. Do you just want to make that again like a bit more crystal clear? What are like the immediate steps that your milestones that you're hitting, and from an investor perspective, what can people get excited about?
Absolutely. I think the big exciting thing about this company is that a very rich and cool person spent like $40 million, and they will take 15% of the company only for everything they've built, helped us build. We're looking for a $10 million seed round. And at that time, we will enable protein structure, atomic resolution prediction, and a battery simulation engine. And we want to close that round sometime in September. It's the usual round. You get 20% of the company for $10 million. And if you need any more details, my colleague Jeffrey and my other colleagues are on the call, and we can tell you we're a company, even though we're a bunch of scientists. We have a data room. You can talk to us. We have real investors and so on. And we have LOIs for people already. Actually, this is interesting. It's very difficult to get big companies to learn to take anything new until it's really popular. But we have a lot of interest from smaller companies, battery startups, lots of protein antibody interaction startups that really want it. They want it now. They want it yesterday.
Love it. Okay, so great that you have the first customers lined up there as well. Okay, is there anything you wish I had asked that we didn't get to? Any bits that you think we missed, or where you're like, oh, we could do another deep dive into that? I just want to make sure that we have everything covered.
I think we have everything. These questions were amazing. This audience is just really like fabulous. This has been really good. I do want to say and give like a minute. This is not a one-person effort just because I'm speaking. So I'd like to introduce some of the team members here. Maybe you guys can say hi, Leonid and Igor and everyone. Just say hi. There's a bunch of people here. You can just show, if you show your faces, maybe the person who speaks English the best, not very well, but not too bad. And they just want to say hi because it is a team effort and these people are amazing.
Yeah. I'm very excited about ATP. Yeah.
That's right.
It was definitely doable.
Yeah. Leo, Alexei, Ganesh, Evgen, who is...
Thank you for your interest.
Evgen is calling us from Ukraine, and Mikhail and Oleg and Ganesh. And I'm sorry I might forget someone, but this is not a kind of thing a person can do alone. There's no way. They did it.
If one were to visit you guys in your offices, where is your...
It's West Berkeley.
From the Bay. Yeah. Cool.
Yeah.
Okay.
Yeah.
Awesome.
Yeah.
You come by there.
Yeah, that's right.
Sounds wonderful.
Yeah. Sounds cool. Yeah, absolutely.
It's really nice to meet all of you. Thanks everyone for zooming in. I really appreciate it. And what a fantastic effort. I'm so excited about the progress that you guys are making so fast.
Thank you.
I'm really glad that you're like incubated now into a company, and it seems like you're doing like wild stuff really fast. Thanks everyone for your amazing questions. Thanks a lot for joining us for a longer presentation. And we will also publish this on YouTube. And I'm assuming that if people Google your name, then they'll also find a way to contact you. That is may or may not have also been on the last slide. Okay, everyone. Thank you so much. Really appreciate it, and have a good rest of your day.